of the Department of Mechanical Engineering, Coachbihar Government Engineering College. And finally, I must thank the participants, okay, so who are there throughout the day to listen to the lectures. So hopefully, you are all undergraduate students, maybe second year, third year, or fourth year. So my topic is that is fluid flow with combustions. This is also sometimes known as also reacting flow. So let me load the file first. Okay, whether it is coming up. Are you able to see something on the screen?
Yes, sir. Yes.
Okay, very good. So that is the topic today's, that is fluid flow with combustion. Now, you have studied the subjects of fluid mechanics, or you will study, and also after that the heat transfer. Of course, thermodynamics is already studied. So in a fluid flow, the phenomena or the things are governed by two equations. One is called the conservation of mass, that is also known as the continuity equations, and other one is called the conservation of momentum, that is basically Navier-Stokes equations. And if these equations are partial differential equations, and you have seen the complexity of these equations, and if there is a heat transfer with that, particularly the convective heat transfer, then of course the energy equation, similar type of equation will come there. So solving of these equations in its full form is impossible because no such initial conditions or boundary condition available. So it is not only very difficult, it's impossible to solve this equation in its full form. So what we did is that we just remove some of the terms from the equations to make it simplified. Of course, with some assumption, with some reason behind that okay, this term may not be that. So then we get some approximate analytical solutions. But to do that, we have to sacrifice a lot of things because otherwise it is not solvable. Then, if we combine with this combustion means, let us take in an internal combustion engine, so the gas turbines, there must be combustion of fuels. So along with combustions, that means another science, not only that is the combustions, chemistry, chemical kinetics, then thermodynamics, along with that, fluid mechanics, heat transfer, all these things are coming in, and the things become very much complicated. Again, but we have some equations for that along with those equations, and then we have to solve them. And as I said, that it is not possible to solve in that full form. So what we do now, the best thing is that if we can do some experiments, but the experiment is not always feasible because it is a time consuming and also not cost effective always. Secondly, you cannot immediately change the parameters. Okay, suppose you want to change the fluid, you want to change the pressure, you want to change the inclination of that particular thing. So all these things will take much time. Secondly, and sometimes the environment is hazardous. That means the fluid itself is hazardous. So the handling of that is also difficult. So to overcome that, so in between the analytical solutions where we have approximated so much, now we don't approximate so much, but obviously again we have to eliminate some terms which are not so significant. Then what we do, we go for a numerical methods. Numerical method means we want to get the solution of that. Remember that these are all partial differential equations. It is not an algebraic equations. So what is the numerical methods? So even in case of your algebraic equations, okay, what do we do? We just factorize and then try to solve it. Then get that. If we don't get, we go for that minus b plus minus root over, sorry, something like that. But even after that, if you don't get, if we put the solution in that equation and if it satisfies that, then we say that is the solution. But that you can get by chance. Now, what we do in an numerical, say algebraic equations, we put some value, we guess it, and also the degree of guessing to the accurate to the actual value is also very important. And then they put it. It is not satisfying. Then what we do? We change it, and then again put it. Okay, it is not satisfying, but it is rather better than that. So in this way we go on, and this changing from one value to one that follows certain rule. I think you know that Newton action and all these things are there. That is called iteration. So I think you have heard in your mathematics or maybe here. Here also we do the same thing. Now this fluid flow problems along with heat transfer, maybe with combustions. So basically it was developed on the basis of fluid flow, particularly say on aerospace industry, etc. That is, we first we try to solve by these numerical methods. So what we do here, and that is called the computational fluid dynamics, CFD, and that is a very good subject for the undergraduate as well as postgraduate study. And if you have knowledge in this, you can do your project, final year project, even your higher study or research in this area. Many people are doing that research on this particular aspects, and some of them are only doing it fluid flow, and some of them are doing fluid flow and heat transfer, and in some cases it can be combined with combustions. So what we do there is that, first of all, you have to, where we get a solution, say some parameters, say temperature is a function of x and y. That is the thing. So if we get analytical solution, then T can be written as a polynomial of x and y. But here we will not do that because it's not possible to get that analytical solutions. What we'll do, we'll divide that where we need the solutions. Okay, say in a pipe, we need the solution for all radius and all length, etc. So we divide this into a very small element, which is called the grid. And at those points, we want to get the solutions. It's not a continuous one at those particular points. Similar things we do in experiment. We get the values at some 4 or 5 distinct points, and then we draw the graph and then interpolate, extrapolate to get the values at the other points. So here also we just divide the whole thing into certain domains, certain points, certain grids, we call it. Maybe one-dimensional grid for one-dimensional problem, two-dimensional for two, and the three-dimensional also. And then we get the solution of the different parameters, relevant parameters like the velocity, temperature, or the other relevant terms in combustions at those points. Now, if the points are very close to each other, that means the grid size is smaller, then what we get? The points will be very close, that is almost your continuous solutions. So that particular process of converting these differential equations into your algebraic equations is called the discretizations. And that has to be done following certain rules. It's not arbitrary, otherwise it cannot convert into the converse solution. Okay, it will diverge. Okay, so let us with that. Now what is here? Okay. So why you are going to combustion also? So I think you know that the major parts of the world energy that we are using is still coming from the combustion of fossil fuels. Okay, that may be solid, liquid, or gas. I think you know the coals. Then you know that liquids like petrol, diesel, kerosene, and biodiesel, ethanol, etc. And of course, the gases, natural gas, LPG, methane, and also it's coming hydrogen. And as the energy demand by the society is increasing day by day, and all these fossil fuels are also limited in nature. So in one day will come when the fossil fuels will be exhausted. I don't know when the date will come, because we are uttering this word from last 40 years, when I was also a student. That is, this will be exhausted within the next 30 years or something like that. But somehow it is not exhausted. But the second problem is that the pollution of the environmental problem, that is a very important thing. So due to the combustions, there are many pollutants which are harmful and toxic, so they are liberated. So like your different greenhouse gases, also NOx, SOx, carbon dioxide, carbon monoxide, and one more talk, I talk about this smoke. Okay, this is also a pollutant from the combustion. So we will talk about this. So whenever we design some combustion systems, we have to keep in mind the fuel economy so that we get the maximum efficiency.
সন্দেহপাতটা একটু বুঝিয়ে দিলাম ওকে আগে আজকে
At the same time,
হ্যাঁ একটু গাইড করতে দিলাম ওকে সন্দেহপাতটা
hello,
দিলাম যে একটা অঙ্ক করে
am I audible to you?
অল্পখানি করতে দিয়েছে অঙ্ক আর ফিজিক্সের ওই কাজটা করে আসেন ওটা করে নিতে নেক্সট দিন 8টা চ্যাপ্টার কোশ্চেন দেবো
Hello,
Rishi, mute your mic.
দিয়ে তোমার দিয়ে দিলাম
Okay.
সময় গতি কিছুটা পড়ালাম তরুণ গতি
As someone is talking, I think I just put ask him to put that mic muted and then. Okay, so that is these two things, that is the fuel economy. At the same time, the pollution, that should be considered simultaneously. And again, these two are conflicting. And these are okay. These are very much dependent. These things are very much dependent on the fluid flow and the temperature distributions inside the combustion chamber. So we must have a knowledge about the fluid flow and the temperature distributions, and that is obviously a case of fluid mechanics and convective heat transfer. Okay. So let's see what is combustion. So as your sir has already described, that is basically a chemical process where a substance reacts with the oxygen or oxidizer. That oxygen may be directly supplied, but in most of the cases it's come from air, we supply air, and due to that the heat will be released, which will be finally converted to our mechanical work employing a heat engine like different internal combustion engines or external combustion engine. Okay. So this is
Sir, the slides are not changing, sir.
Mic is not?
Slides are not changing, sir.
Slides are not changing. Okay, so let me go to the other one. That is the problem with that. Okay. If this is the case, what is the problem here? Just a minute. So I am using some another one. So let's see whether. Can you see now?
Yes, sir. Is recommended books slide number 93.
That is the last slide. Okay, come to that. Let me start from the beginning. It's like this. Just a minute. I think now I have gone to the slideshow. Now, is it visible now?
Yes, sir. Yes, sir. Visible.
Changing. Slide is changing.
No, sir. Still on one number.
Why this is happening? Just a minute. So now it has changed or not? Changing?
No, sir. Yes, sir. Slide number 2.
Yeah, slide number 3. Right here we are.
Yes, sir. Has changed.
So, but actually, can you read this?
Yes, sir.
Okay, let's see. Okay, so that is about the fuel, which is the combustible material, and the source of the oxygen is normally air. Okay, the fuel can be, as I told you, that solid, gas, or liquid, and sometimes the light is also given off, either in the form of flame or a gas. It has changed or not? Hello,
No change, sir. No change, sir. Slide number 3.
is not changing. Slide remains as it is. The slide remains as it was. It is not changing here.
Yeah, it has
Change,
changed
sir.
here? Okay.
Yes, sir.
When,
Change.
when I'm going to the presentation mode, it is not changing. Anyway, let us stay here only. So that is, so whenever you combust something, so there will be flame formations, and normally there are two types of flames. And we also said that the combustion in that particular mode, one is called the premix mode, and the flame is called the premix flame. Other one is called the non-premix mode, or the flame is called non-premix flame, or also sometimes that is called the diffusion flame. Okay. Now that both the flames can be turbulent and laminar, you can see on the right side that some of the applications of this. So from the premix flame, that is the one of the common example is the Bunsen flame, and for the turbulent, that is whatever is happening inside the petrol or the SI engine. Now, if you go to the diffusion flame or the non-premix flame, you can see the turbulent cases will be in case of candle, that is the diffusion flame. Okay, I'm coming to that. What is that? Wood and the radiant burners. Now, sorry, the premix flame means before the combustion means we need both fuels and the oxidizer. If they are mixed previously before it enters into the combustion chamber, then we call it the premix flame, and that happens in case of SI engine. So normally it is mixed in the carburetor. Okay, so nowadays of course carburetor is very obsolete anyway. So they are mixed beforehand before its entry into the combustion chamber. So in the combustion chamber, the mixing is not important, only the chemical reactions, the chemical kinetics is important. But when you talk about non-premix flame or diffusion flame, where initially both the fluid and the oxidizer or air, they are separated and they are entering into the combustion chamber, they are diffusing to each other, and then there is chemical reactions. So there is a diffusion, and that's why it is called diffusion flames. Obviously, it is not only controlled by the chemical kinetics, rather the diffusion process is also important. So now let us see that the common examples of premix flame. You can see here, this is the Bunsen burner. You can see that from the bottom, the fuel is going here and the air is taken. But in this chamber, they are basically mixing. So that is then the mixing chamber, in case this is this one. And then this is the combustion chamber where they will go after mixing. So that is called the premix flame. Now look at, let us see, this is a diffusion flame or non-premix flame. So what is happening? You can see there is a central hole through which the fuel is coming. So you have a separate tube, and surrounding that there are lots of small tubes through which the oxidizer are coming. And after that, when this is the combustion chamber, so when they are coming to the combustion chamber, then they are mixing and combusting. So that's why it is called diffusion flame. So our discussion will be mainly on the diffusion flame, and this is important. So as I already told, so now diffusion flame, that is any flame in which the fuel and oxidizer are initially not mixed, rather separated. So there are some applications of this, very important applications in gas turbine combustors, internal combustion engines, like your diesel engines, then of course different industrial furnaces. Now let us come to this chute. As I told you that I talk about this also, because this is a very important pollutant. So that is generated due to combustion. And the amount of chute generated in case of SI engine or premix flame is normally less, but in case of this case, diffusion flame, it is more. So what is chute? That is basically tiny carbon particles, that is carbon particles, very, very small carbon particles. During complete combustion of the fuels, they stick together and they form the chute. These are very, very small size. Sometimes you may not be able to see it unless they are agglomerated together. So, okay, this is not good for our health because it can problem in inhalation, and there is a problem in bronchitis, all these things, when there all other problems are there. So this due to that, so chute formation mechanism must be known, and then how to reduce that. But unfortunately, the chute formation mechanism is not properly, still not fully understood. But there are some models out there. So now these are the things that happens that people are telling in a chute formation process. That is, the first thing is that there will be chute formed, and since chute is basically carbon, so they will be oxidized also. That means that chute will burn down. Now, depending upon which one is more, so that will remains. If the chute formation is more than the chute oxidation, and that is the normal case, so we get a lot of chute. So now there are 4 processes people are thinking like that. That is a nucleation or inception. That is a small nucleation, and after that, that will grow in size. That is called the surface growth. And then some of the shoot will coagulate. That means they will, a number of shoot particles will make a single particles. That is called coagulation. And finally, some of them will oxidize. That is called oxidations. Now, this is somehow that if we show it, that is like this. That is, so we are taking the hydrocarbon fuel, and then that is called pyrolysis. That is basically the breaking of that fuels in the absence of very small amount of oxygen, and we get the smaller hydrocarbons. And then in between they will be converted to acetylene, and then acetylene will form that aromatic species. And then finally this is PAH, what is called polycyclic aromatic hydrocarbons, and that is the shoot inception. And when this size increases to at least 10 nanometer size, we say that it has been created or formed. Okay. So next is, so now the mathematical model. Okay, what is that? So the mathematical model, now as I told you that we do it by computational fluid dynamics analysis or numerical method. So then we have to get a mathematical model. What is that? That is basically the mathematical description of the physical problem, and that will come ultimately in terms of equations. And we have to solve those equations subjected to some known boundary conditions. So what is that? Now let us see. So let us see the physical model. Okay. Now the physical model, okay, it should be based on some physical model. Now what is the physical model? So basically, two concentric vertical tubes we are considering. That is the burner. So the inner tube, the fuel that we consider in this particular case, their methane, will enter, and through the outer tube jet, annular jet, that is outer one, through which the air will enter, and we are calling this as co-flowing because they are entering, flowing in the same directions. And the diameter of the inner fuel tube is 12.7 millimeter, and the outer tube diameter is 50.4 millimeter. And we take that length 30 centimeter of that where the combustion chamber. So that is, they are entering separately into the combustion chamber. And I am not able to see these things anyway. So now as I told you that you have to consider, don't get nervous with the shape of these equations. Now, since we are considering a cylindrical things, because the tubes, two tubes, the one is inner tubes, other is the annular tubes. So we are taking this as your cylindrical coordinates, and you can see that the parameters will vary in the z direction, the axial direction, and also in the radial directions. It will not vary in the theta directions because, and that's why it is called axisymmetrical. In all theta will be the same. So that's why you are considering two-dimensional equations. So I think some of the equations are known to you. Okay, forget about that. So this is called the mass conservation equations in cylindrical coordinates. So the first term is that is del rho by del t, even in this one, and that is the unsteady term. Okay, forget about that, those things now. And this is the radial momentum directions, radial momentum equations. That means momentum equation in the r directions, and we'll have also the momentum equations in the z direction. And I think you know that in the momentum equations there are few terms. The first one is called the unsteady terms, second one is called the convective terms, third one is called the diffusion terms, and the fourth one is called the your source terms. Okay, so that you will be able to write down afterwards. Okay, so this is called the axial momentum equations. Now, since there is a change in species due to combustion, some species are consumed and some new species are formed. So we have to have the species conservation equations, that is all the species involved in this particular combustion process. So that's why I have given that J, you can see Cj, that is the concentration of that particular J. So J is equal to from 1 to the number of species. And this another equation that is dJm, that is the diffusion coefficient. So how they are diffusing each other. And the last one you can see that is the S dot Cj, that is called the source term. That is, you have to add also how much amount of a particular species is formed and how much amount of that is being destroyed in chemical reactions. That can be obtained from the chemical reaction. I'll come to that. So then, okay, now let us see this one. What is the equation that we will consider? Now, methane and air. So that means basically methane and oxygen. So the reaction is very simple. I mean, that is, we know the reaction, that is the methane plus oxygen is equal to carbon dioxide plus water vapor. But that is called the global reactions. And it will not happen in that way. There are so many intermediate reactions and so many intermediate species are formed. So there are the list of equations, number of species are very large in an actual case. In the literature, we find even 64 reactions are available in between that. And obviously more than that species are also involved. But that will again make also the things very, very complicated. So only the commercial software which are dedicated to the chemical reactions that is needed. So to keep that flavor of intermediate reactions, we have taken two equations, that is two-step combustion of methane, not the single one or the global one. So at least we get one step extra, and obviously in this way, some in between things are also, that is carbon dioxide, etc. have been formed. Okay, then the formation of particular components, a particular species, that can be obtained from the RNAs type rate equations. Okay, this is given by this. Okay, this is slightly not complicated, but you have to go to any other computed. So from that we get that how much amount of one particular species is formed. Okay, then here that is the source term of the species conservation equations. That can be, I mean, that is, you can see from K1 to 2, that is, here the number of equations are 2. If there are more, then for each reactions, you have to get the amount of that species formed. So somehow from this 2, we are only getting 4 species. That is, in our subsequent simulations, we will get methane, oxygen, carbon dioxide, CO, and H2O. And of course, since we are supplying here, so nitrogen will be obtained by difference. Now, this is again. So now, what will happen after the chemical reactions at different points, or rather different grid points I'm talking about? That is, you have divided the whole zone into different grid points. So at different points, the temperature will be different, velocity will be different, pressure will be different, and also the species that will be remaining there. There may be carbon dioxide and water vapor and carbon monoxide, but the percentage of that vary. Okay, and then at that particular point, the enthalpy will be the enthalpy of all the things together, and that is taken care by this. That is, you have to calculate the enthalpy of each component at that point corresponding to the temperature by this equation HF0 plus integration of C dt. So this is called the heat of formation, and that is the sensible heat. So that is corresponding to that, and multiplied by the mole fraction. So that is basically weighted average we are taking, and that is giving you the total enthalpy of the at that point. Now, the energy equation that I told that, in addition to that, we need energy equations. So energy equation may be written in terms of temperature or in terms of enthalpy. So here you have taken the enthalpy. And you can see here also the structure of the equation is similar to other equations. Only thing is that the different terms are different. Anyway, so we will not go into details of this. Okay, then these important properties. Okay, that once we get the solutions for enthalpy, then since there is an equation connecting enthalpy and temperature, we have already shown. So we will be able to find out the temperature of the gas mixture by that calculations of using Newton reduction methods by an implicit method. Now these parameters, that is the viscosity, thermal conductivity, and mass diffusivity, are also very important because that is already there. So these can be, okay, that is we have they are considered that this property will actually the vary with temperature. So that variation is also taken care. So you can see that viscosity is taken like this. Means you have a standard one, that P by P0 to the power P, and the P is equal to 0.7 that is taken from this previous one. So that is for a particular thing, and then we have to find out the viscosity of the mixture at that point by a semi-empirical method, which is known as your Wilkie method. So that is something like some average type things. Similarly, the conductivity also for each we will find out, and then again we will go for that type of semi-empirical method to get the conductivity at that point, right? And this is also for the mass diffusivity. So all these things once are obtained, I mean the variation is taken, then okay. Now see, as I told you that shoot formation is also not fully understood, but many people are doing it based on their experimental things. They have used some which is called the semi-empirical model. So one of them is by Serev et al. And this was, and in the case of shoot formations, how do we express the shoot? That is, two parameters are taken, that is called shoot volume fraction. That is, what is the volume of the sheet out of the total volume of that particular bead. That is very, very small, but that is important. And the number density. Shoot number density, how many shoot particles are there in per unit volume. So these two are the variables. And as I told you previously, that there are four phenomena: nucleation, surface growth, coagulation. Oh, sorry. So these are the phenomena: nucleation, surface growth, coagulation, and oxidation. These four things are taken care in the model. And afterwards, as I told you, there is oxidation. So due to oxidation, shoot will be reduced because shoot will be burned out. And there are several models again are available for the shoot oxidations. Now we have taken from 1962 model. This is due to the limitation of our things, because we didn't take much details kinetics. Okay, because we have considered here the oxygen to be the oxidizer, but OH that is also formed in an actual combustion process, that is also a very good oxidizer, but we cannot take that because in our equations that we have considered for combustion there is no oxidation. So this is the model by Lee et al. So that is given by this. Now let us see here. So now shoot volume, that is FG, that multiplied by rho S shoot density, that is called shoot mass concentration. So that is the variable. And you can see there are, the first term is called the surface growth, second one is nucleation, and this is negative term, that is called the oxidation. Because so the shoot volume or shoot mass concentration will depend on the nucleation, surface growth minus the oxidation, the amount of shoot that is getting oxidized. Similarly, the shoot number density, that is n by n0, n0 is Avogadro's number, is dependent on two things. That is, shoot number means how many shoot have been nucleated, and then when there is a coagulation, that is some of the shoot particles become one, so then there is a decrease in the number, and that's why that minus sign is there. And the density of shoot is taken to be 1800 kg per meter cube. Okay, these are the different, I'm not going into details of that. So these are the different values, that is alpha, beta, gamma, we have taken there. So that is taken from the literature like that. Now, one more thing is that then the conservation equation of shoot mass concentration. So whatever previously I have shown, that is the source term that I told you, that there is a source term, which is denoted by S phi dot. You can see this. So this is a general equations. Having the first term is unstable, second term is your convective, and the third term on the right hand side, the first term is your diffusive. So here, the shoot does not follow the normal velocity, it follows the velocity which is called the thermophoretic velocity, and which happens due to the temperature difference across this. And this is given by a particular parameter. So where zeta is called the accommodation factor, it is taken 1. Okay, so now let us see again what we have done here. So this is our model. Okay, you can see. This is this inner one, that is, you can see the fuel is entering to the inner one, and outer. Okay, this is basically called confined because the outer thing is also closed. Now air is entering, and they are diffusing, and after combustion, this is the flame. So this is the center line. Okay. Now it is very clear that on the right hand side and the left hand side, the phenomenon is same. Whatever you get, whether you get the velocity or temperature or shoot, they will be exactly same, rather the mirror image of that. So we did the what is called the simulation only on one side of the central axis. Now this is the only right side, because left side is similar, exactly similar. This will help you to reduce the times. Now, as the number of grids increases, this is very clear. You can see number of grids increases means it is called a fine grid. That is the very close grids. The accuracy will be better, but the computational time will increase. Then you have to take an optimum size. And obviously, if we simulate both the sides together, it will be simply double. So, since it is exactly the same, there is no need of doing. And this is called the grid structure. Now, this portion, that is the center line and the other side, this has been divided into number of grids. Okay, so the grid may be from 4 to 5 to maybe lakhs and 10 lakhs like that. So that all depends. So initially, when this technique was discovered, so the people when there was a hand calculations, very less number of 4, 5. But now with the availability of very fast computers, we can go for lakhs, even better than that. So, but it is also very clear that that will give you the computer time more. Now, you may not be able to judge the computer timing by solving simple problems, because that will give you immediately. But when you give means, I mean, that means you have to do the iterations over 1 lakh points, so it will take much time. Now, you can see the black portion means it is not black. There are also grids, but they are so close to each other that they are seeing the thing. But here you are able to see that the grids are coarse. That means the number of grid size is less. I mean, size is more. And this is done intentionally, where the chances of variations of the variables are very high. There we take the fine grids, obviously in the center, and when the flame is the combustion is taking place just after the burner. This is the burner. Okay, I mean, where through is entering. So that's why this is the grid size. Okay, now this is also very important. That is the boundary condition. So whenever you want to solve any computational fluid dynamics problem, so you have to first identify the boundary conditions, because otherwise, those are equations. I think you know that in any differential equations, if you solve and if some initial conditions are not given, then you have to write plus C1 or C, and that C is evaluated after putting that initial condition or some condition. That is for this X, this is the Y. So here also, we have to know from our experience what are the boundary conditions. Now you can see, say Z directions. If you go back to this, Z direction means that is Z is equal to 0, that is where both of them are entering, and this is Z is equal to this length, which you have taken as 30 centimeter, which is good enough so that it becomes steady there. I mean, there will be no variation after that. So Z is equal to 0. Out of that, there are 2 R, that is R, that is the inner R, that is through which the fuel is entering, and beyond that, the air is entering. So you can see, R is equal to dF by 2, that is inner one, inner fuel jet. So here, the fuel is entering. So what you have to give? Rho is equal to rho fuel, that is fuel density. Vz is equal to Vf, the velocity with which fuel is entering. And we are assuming that that is entering axially, so there is no radial velocity in R direction, that is Vr is equal to 0. This does not mean that after there will not be radial velocity. There will be radial velocity because there will be other phenomena. And T is equal to Tf, the temperature of the fuel with which it is entering. And since these are the concentration of the different species, so here it's only fuel. That's why Cf is equal to 1, and you can see that oxygen, carbon dioxide, carbon monoxide, and water vapor all are 0. Now go to the other one, that is the outer one, that is the annular jet through which air is entering. There is no fuel. So that's why we give rho is equal to rho of air. We are again 0, it is again entering axially. Vz is equal to Va, the velocity with which velocity is entering. That may not be same as that of the fuel, because that depends on the mass of the fuel that is entering, and of course the cross-sectional area through which it is entering. and T is equal to TA, the temperature of the fuel of the air. And if you go to the concentration, there is no fuel, CF is equal to 0, and whatever you have written here, that is basically the, that is the composition of the air that is having this is the oxygen. There is no carbon monoxide, no carbon dioxide, water, vapor, only the nitrogen is there that we are not considering. Now for all R initially, where here, when it is entering, that is at Z is equal to 0, there is no shoot volume fraction, if V is equal to 0, no shoot particles. Okay, we are not considering for the time being there is NO. So it is entering without any shoot, so that's why shoot volume fraction is 0, shoot number density is also 0. Next is the outlet. As I told you that at the outlet, it is fully developed. That means all the derivatives of the velocity, temperature, concentration, shoot volume fraction, number, density is 0. At the axis, that is R is equal to, that we have given for J, now R. At the axis, that is the radial symmetrical. Axis is symmetrical. So there cannot be any veer, that it cannot go from this side to this side. And also, this derivative will be 0 for all the other parameters. At the valve, what are the conditions? Pz is equal to 0. What is that condition? That is called the no slip condition, the famous condition in fluid mechanics. And Vr is equal to 0. That is impermeable condition. It cannot go beyond that valve. And also these derivatives are 0. Now sometimes, if there is a recirculation of air from the top, then the composition and the temperature of the fluid entering the computational domain at the exit plane is same as that is outside there. So these boundary conditions are given at the boundary, and this information will propagate throughout the computational zone following the rules of fluid mechanics or heat transfer that is given by those equations. Those are known as, that's why, governing equations. So that will follow that governing equations, and this information, slowly that will be propagated, and finally, when it is fully propagated, we say now we are getting the final results of the steady state. That is the outcome. So now, okay, now since we will do some numerical, we have to give some numerical data, that is, as I told you, that the temperature, etc. So we have considered two air temperature. That is, one is 300 Kelvin, one of them is 400 Kelvin. 300 Kelvin means that is the normal, 25 degrees centigrade, around something like that. And that's 400 Kelvin. I think you know that if we can supply preheated air, then the combustion will be better. And that is the reason for employing a air preheater in a boiler plant. I think you have studied that after the economizer, there is a air preheater where the incoming air, instead of going directly into the combustion chamber, for combustion of coal, that is slightly preheated with the exhaust gas, which is otherwise than wasted. So we see that also. Fuel inlet temperature we are keeping fixed, 300 Kelvin. Okay, you can vary that also. Then the fuel flow rate is 3.7 into 10 to the power minus 5 kg per second. And from that, if you calculate the geometry, that is your density and whatever is there, area, the fuel jet velocity at the inlet is 4.5 centimeter per second. Similarly, air flow rate is this, and air jet velocity at the inlet will be 9.8 centimeter per second. But when it is preheated, then the density will decrease, but the mass flow rate will remain same, area remaining same, so the velocity will increase. So these are the things, and you have to, combustion has to be started. That is called the ignition. Okay, so now in the physical problem, we ignite it by spark or whatever it may be, or by some burner. But here, what we do, we just, give the temperature of few cells, few grid points up to 100 Kelvin initially. So, and that will be given in the form of enthalpy corresponding to that. And once the combustion starts, then we draw that. So then it will be self-propagated. So that is the ignition. Now, how we will solve this? So that we have said that is, okay, there are several methods in computational fluid dynamics. So one of them is called the finite difference method. There are explicit, implicit. So we use that explicit finite difference method. Of course, there are finite volume methods and there is also finite element method. And finally, so it will generate the following variables which are important for our assay. That is the velocity, temperature, species concentration, and 2 terms for shoot, that is the shoot volume fraction and shoot number density. Okay, and as I told you, this solution you have to follow some algorithm. Otherwise, it cannot reach the final. You won't get the solution. Okay, it will divert. The computer is slow, hang. So there are very famous one that is called the simple algorithm. So that you can start with that. But here the algorithm is called solar algorithm. Here the primitive variables are used. So primitive variables means we use that UV and then temperature, T, pressure like that. But in many simulations, it is obtained in the form of non-dimensional form. Now the variables are defined following a staggered grid arrangement. So this is important because we have got a grid. And at the center of the grid, we just get some values, and at the face of the grid, we get some values. And there are some difficulties, that's why it is done. So we will learn it from afterwards. So normally at the center, the scalar quantities like fluid properties, etc., are obtained, and at the grid surface, we get the velocities. Now the solution is explicitly advanced in time in a steady state conversion. So once the combustion starts at some time, then we'll see what is happening after 0.01 second, after 0.this second, and finally a time will come when the things will be steady. We call that is the steady state solution. And before that, there is a early transience. Okay, as I told you that the grid size, this is very important. Already have discussed that depending upon the grid size, the accuracy, at the same time, the computation time will be different. So as I told you here, the grid size will not be uniform. Rather, you have to take the fine grid at the points where the variations is more, and where the variation is not more, then you can take slightly poor grid. But of course, this variation in the grid, I mean, the size will not be sudden. It has to be done gradually. Okay, this thing also you have said that you have to discretize this. That is, you have to get the algebraic equations which you will solve finally. And there are different methods like the central differencing method, and there are others. Okay, we'll not talk about this. So there is a discretization method by which you have to do it. So if you can start it, then only you will be able to see this. Now, what will be the time step? As I told you that we advance in time. We will give the equation after some times. We will get the situation after some time. And this time increment should be such that it has to be done from 2 points. One, the advection, or that you can say some of convection time. That is, should not convey a fluid element past a cell in one time constant. So it has to be taken so small that in that time it will not pass a small cell that we are considering. Similarly, another condition from the conductions, that is this one, and finally the minimum of that will be taken, and to ensure that is again minimized. Now another important thing, that is the grid independent test. So as I told you, as we increase the number of grid sizes, we find that results will be improved, but at the same time the other things will also increase. So with different sizes of grids, so here is the 2-dimensional grid, so 85 in the axial direction, 41 in the R directions. Similarly, another one is 121 and 61. So if we increase the grid size from that to this side, we find that there is a minimum 2% change in the result, but at the same time it is taking twice the computational time. So we not go for the higher side for 2% improvement. So we take the 85 by 41. So that is your choice. That is whether you can get 1% more better result using more computed time. So in this case, 85 into 41 in the Z direction 85, and the and the R direction 41 loops are available. So if we plot this, the results with 121 and 61 cells and 85, you can see that they are very close, just to show that it is independent. So what we are showing here, the radial temperature distribution at 12 millimeter above the burner. So if the burner through which the air and fuel are entering the height that is taken as z is equal to 0, and above that we are considering from z is equal to 0 to 30. So we are 30 centimeter. So we are going to 12 millimeter height, where we are showing a 12 millimeter plane how the temperature is varying in the z directions, r directions, radially. So that is radial direction is up to 0.24. So this is the thing. So we said that okay, this I will do. Now another thing is that, as I told you, the experiment will give you the most accurate results if you can do it properly with proper equipments. And whatever code is you are developing, there are some uncertainties. That means you are not able to consider all the things. You have to compromise somewhere. But the results should follow the experimental results, at least qualitatively and sometimes quantitatively. Okay, maybe in a numerical methods or numerical study, 10% variable is allowable, but it should not be, trend should be same. So that's why this is validated with the experimental results that is available by Beecher et al. In 1980. You can see all our dimensions, that is, we have taken the dimension, fluid flow rate, etc., mass flow rate of the air, and fuel from that corresponding to that. It's not that both values have come arbitrarily, because ultimately you have to compare with that. That's why you have taken those values. And we have seen that is the good agreement is there. Only the temperature is over predicted, and the flame is found to be little closer. Okay, another thing is that same height. So now let's see how what it is. Now you can see these dotted lines, I mean these discrete points are the experimental values, and our whatever we in the predicted values we got this one. Okay, so they are not exactly same, but okay, they are matching. That is for temperature. And here we have done for carbon dioxide and water vapor. So there are also some deviations obviously there, but as I told you, this can be allowed in numerical methods. So with that okay, our code is predicting right values. So we will go to the other things. Okay, similarly, that food formation model that we have considered, you can see here. So that is also validated with an experimental work of Smoke et al. Smoke, that is, he is one of the pioneer in the shoe formation study, etc. So here you can see again the present value is this one, this is the experimental value of that fellow, and they have also predicted something. So our one is in between that. Okay, you can see that the experimental value is not available throughout the length, only in the smaller zone. And another one is on another height. So this is again. So then you can say that it is also in more or less qualitatively matching the experimental value and sometimes also quantitatively. Now we just show some results. Okay. So now we'll give ignitions. Okay. And we'll see after what time we get a steady flame. Now look here. So under the steady state, that is being reached after 0.8 seconds after the ignition is given in case of non-preheated air, where the air temperature is 300 Kelvin, and it will take more time, 3.2 seconds, where the air temperature is 400 Kelvin, that is the preheated air, because there are some more complications in the fluid flow, etc. is there. Over-ventilated flame in both the cases. Over-ventilated flame means the flame will be towards the center line. And huge difference in the steady state flow pattern and temperature contours. But if you look at this, you'll see that afterward, the velocity and the temperature, there is a huge difference. Now let's see that. Okay, now these are called contours. Okay, contour means this is the temperature contours, that means along this value 400, all these points on this 400 Kelvin, and beyond towards the right it will be less than that. So this is 800, and in between. These are the, to show that normally in the form of contour is shown. You can see we have started with 300 Kelvin here and 300 Kelvin 12. You can see towards the right of this, our temperature is almost 300. So the isotherms are vertical. And if you look at this one, that is the dotted bold line, that is for the flame. You can see it is something like slightly more than 11 centimeter. Okay, 11 centimeter, 11.5, something like that is the flame height. Okay, this is this side and other side will come the similar thing. So that will give you the flame because we have. Hello, hello. Okay, so now this one is the velocity distribution. Now velocity is normally shown either by plotting streamlines or whatever you have shown here by plotting the velocity vectors. Now what is velocity vectors? Now these are the velocity vectors. You can see the length will give you the magnitude and the arrow will give you the directions. So if you look very carefully, the velocity here is increased. And here there is a recirculation, that means from the top side towards the right, air is entering through this. So that is happening, and due to buoyancy and etc. here, because the combustion takes place mainly here, this will go up. And this is the case, just want to compare. Now if you look at the preheated air, you can see now the temperature contours are more uniformly spread. You can see 1200 Kelvin also towards the wall, but that was not there in previous. And also there is no recirculation. There is nothing is entering through this, finally going up. And here also, this is the flame height, which is slightly less in case of preheated air. Now here just I'll go very quickly. So how the flame is developed? So air and fuel, they are allowed to flow sometimes, and then the ignition is given. And after ignition, you can see that 0.05 seconds, this is the flame just initiated. This is the flame after another time. This is the flame after this time. Now you can see even after t is equal to 0.4 seconds, it has been steady because there is no difference between this and this. But since it's a numerical problem, the other variables are adjusting to get the converse solution. And of course, there was some extra flame was seen due to some other reasons. And this is the flame development for 400 Kelvin. You can see the peculiar shape in between. And here also, it is almost, even at t is equal to 0.4 seconds, the flame is almost same. And what you notice that the flame size is slightly less in case of preheated air. And if you look at the, now at different times, how the velocity is changing. Now let's see, this is the initially. Okay, all the things is going up. Then at the 0.5 seconds, you can see that there are some infringement of air from the bottom because the combustion has been initiated. So these are the temperature contour. You can see here also a very narrow zone. Now it has developed more. Now you can see that there is a formation of vortex here. Okay. And finally, okay, that is the final shape. This is the final shape, which is same as our steady state. Now here, in the preheated air, it is much complex. You can see that here two vortices are formed. Anyway, so whatever is written. So you can see that is here is the close to the center line one vortex and close to the wall, and there in the opposite sides. Okay, we have shown that rotation. Okay, and this is now they are trying to flow through the passage in between the vortex, and that's why you can see that they are much bigger velocity vector is here. And this is the temperature we discussed developing. And finally, you can see there is a vortex on the outer wall, but that will be with time that will be pushed away, and finally there will be no vortex. I mean no air circulation from outside. So this is the flame development. So normally we also define a term which is called the bulk mean temperature, and that is given by this expression. And if you plot Another thing is that the center line temperature is very important. So you can see how the center line temperature is changing. Initially it is increasing with time. At t is equal to 0.05 seconds, this is going up to this and then decreasing because it is not propagated. But after some times it will be same. This is the bulk mean temperature. I just go to the, and this is for this thing. Now let us say here the shoot. Now the shoot volume fraction is, you can see that it is in the range of 10 to the power minus 8. So again you can see that at t is equal to 0.5 seconds, the shoot volume fraction, you can see these are the again shoot contour. So maximum value is 1 to 10 to the power minus 8. At this time it is 40 and it has got like this. Here it is 60 and finally it is 40. So finally after 60 it is decreasing to 40 due to oxidation, etc. And all the shoots are staying, not going beyond the flame. This is actually total shoot volume, how that is, I mean, you can see that with time how they are changing, that is increasing. And after some time due to oxidation, there is a balance. When shoot formation and oxidation are same, so they are remaining same. And here also the shoot particle number is also becoming steady, but after a larger time, longer time, it will be steady. Okay, and we can also calculate the shoot diameter. That is also very important. Just considering the shoot particles to be spherical. So you can see that is the 4 nanometer maximum here. Here it is 10 nanometer. And then at 0.15 second is 8 nanometer. So finally the maximum size is 8 nanometer here. This is very important. Now look here, the center line temperature and center line velocity. Center line velocity means that at r is equal to 0, that is the separating this axis, the axis. At r is equal to 0 for different j, that means as it is going out, what is this? Let us say the temperature. Temperature is almost more or less same, but with the preheated air, it will be slightly higher, obviously, because the more heat is available here. But look here, the center line velocity with non-preheated air is much higher, but it has reduced in case of preheated. And the simple reason is that in case of non-preheated air is entering from the exit section. Obviously, that has to be to maintain the continuity. The velocity where it is going upward, that is near the center, that has to be increased. And that will give you another thing. That means the things are remaining for a longer time inside the combustion chamber. As the velocity is less, the residence time will be more, and that will create a favorable condition for soot formation. And that's why the soot formation will be more in case of preheated air. When you use preheated air instead of this. Okay, so that is because we have shown that is the 10 nanometer. Here actually you can see finally is at different times is happening, and you can see that 160, that is not much more. Okay. I think we'll be getting bored now because it is okay that we have compared here. That is okay. This is basically a comparison, just at a glance. These have already been discussed, but here you can see you have plotted. That is also a very good technique. In this, you have plotted three things. That is the flame. This is the flame. Then the temperature contour and the velocity vector. And here also you have plotted the same thing for air preheated air. So at a glance, we will be able to see all the three parameters here, and we can compare. Here also you have shown the soot volume fraction, and that is to show that it is almost 4 times soot formation taking place in the preheated air. And here also we have shown that at different height, as I told you, that most of the soot beyond the flame there is not much soot, practically no soot. So our flame height was around 11 centimeter in case of non-preheated air, and it is slightly less in case of preheated air. Now, if you look here, we have plotted at z is equal to 0.2 meter, that is 2 centimeter, and then Z is equal to 0.4 centimeter, and the red one is with preheated air. You can see that there is practically no fluid in this case. It is there, it is more with preheated air. If you go to the next time, that is 6 centimeter, you can see food formation has increased. At that height is more food is available and more with preheated air. Then is equal to 0.8, the situation is same, and it is much more with preheated air. But when you go for so Z is equal to 10 centimeter, you can see now they are comparable, and Z is equal to 12 centimeter, there is no shoot in the preheated air, but there is some shoot, because this value is beyond the flame length of this preheated air, and that's why no shoot is available. Okay, so whatever I have described, I think this is, you may not be follow this, but at least overall things are clear to you. Obviously, you have to go for further study if you are interested in that. Nothing is difficult, but anyway, let's see what we have described, just an overview of that. Forget about all these equations, discretization graph, etc. So what you have seen, transient as well as steady state temperature fields are greatly affected by reactivity. So that you can see. Whenever you use preheated air instead of non-preheated air, the flow field, that is the velocity distribution, as well as the temperature field will change. And there is a, change means there is a pattern change. Not only that the value, the pattern change. With non-treated air, only one vortex is observed during the entire development process. But with preheated, there are 3 vortexes are formed. And that's why it's become complicated. Flow is slowed down, so it is taking much more time to reach stable. In steady state, large recirculation adjacent to the wall from the outside is observed in non-treated air. That I've shown. Towards the outside, the air is entering. Higher isotherms are observed near the wall. In case of non-treated air, we have shown that beyond certain value of J, the temperature becomes less than 400 or even to the 300 temperature. So only in the wall, in the axis zone it is there, near the wall it's not there. There is no substantial difference in the distribution of steady state central line temperature. So that is thing. And now another thing is that summary of shoot formation. So what we have done here. So one thing I have said that the values of shoot volume fraction, shoot, and the particle number do not reach their peak simultaneously. That is one thing. In preheated air, okay, the qualitative trend is same, but it is obviously more. In fact, the peak shoot volume fraction increases more than 5 times for an increase of 100 Kelvin in the inlet air temperature. All the shoot particles get oxidized in the post-flame region, and the flue ash and the exit one contains. So these are some of the conclusions. Now you may say that then why not preheat up to 500 and 600 Kelvin? Okay, there are problems because mathematically, at least we couldn't do it, maybe done. Okay. So whatever I have described, that may not be what is called, because since you are an undergraduate student and not even exposed to any project, so if you are not ready with that, I mean, after getting this information from here, if you are interested, you can study. And computational fluid dynamics, that is one of the most important subjects. So I think it is there maybe in your curriculum as elective subject in the 4th year or somewhere. So if you are interested in that, those will be working in that research activities or maybe in some computational field. They will be beneficial. So now I'm giving you the books, recommended books, so numerical heat transfer and FluidFlow. This is a book by S.V. Patankar. This is written in a very nice manner, and the book size is also very small. So you can, those who are interested in CFD can study from here initially. It is written like a story, and that is a very popular book also. Then of course there is another book, Introduction to Computational Fluid Dynamics, Finite Volume Method, Bursteck and Morasikala. And for the combustion, I suggest you to go through these books: An Introduction to Combustion, Concepts and Applications by Stephen Starnes. So that is a very good book, written in a nice manner. So you can read these books. So thank you for listening to me for more than 1 hour. It is very difficult to listen to somebody for more than 1 hour. But anyway, you have listened. So with that, I'm concluding. So if you have any question, and there should be questions, don't hesitate to ask any questions. Any questions, when I'm related to this, you can ask. Okay? So let us go through that. So thank you very much. So my delivery is over. Now let us have some question answers. Professor Chatterjee.
Yes, sir. Sir, thank you, sir, for your extremely valuable presentation. And I would like to invite students or anyone having any question, please ask us.
Because it is very.
Okay, if you don't have any question, then I would like to say thanks a lot, sir, for your extremely valuable presentations. And student has learned so many aspects of fundamentals, I mean combustion and combustion flames, different types of flames, means whether it is whether is it diffusion flame or premix flame, and particularly sir has also discussed some CFD and that approach, simulation approach of particularly diffusion flame, and he has done some mathematical modeling on different species and shoot formation also. What we have learned from that lecture, that shoot initiation, then shoot growth, surface growth, and then also that agglomeration, or then also that shoot oxidation, different stages of shoot formation, and also that reduction, and those and also different simulation approaches. When that exact numerical solutions are not there, then trial and error, and those that simulation, that numerical methods also, these things, and experimental validation of this type of claims. Sir has also demonstrated nicely that different temperature contours and that velocity contours of these flames also, and that regions also he had done some finite volume or finite difference methods and these things. And if you any student having any question, this is very much pertinent topic in combustion research. So extremely valuable lecture sir has delivered, which has really enlightened knowledge, thoughts and ideas. So students may also be stimulated to do research in the domain of field of combustion, and that so thank you, sir, for your extremely nice presentation. And last but not the least, I would like to convey this microphone. I want to hand over this microphone to one of our first year student, Miss Madhurima Munshi Kormokar, to give vote of thanks to Professor Dr. Bijan Kumar Mondal sir, who has really taken his nice initiative to deliver lectures in front of our student audiences, which was immensely valuable to our young students. So Madhurima, please.
Yes, sir.
Yes, Madhurima, just 1 minute. So the thing is that, so some of you will obviously come for higher study maybe. So some of you will obviously come. Just a minute.
Sir, from your another.
So some of you will obviously come for higher study to IITs or maybe NITs or maybe even Jadavpur or IST Shibpur. So some of you must be interested, and if there is no questions, that means the lecture is not Okay, so I expect some questions. There are 99 people attending this. So from your level, you ask question. Okay.
Sir, hello.
Uh, uh,
Hello. Am I audible
yes.
to you, sir?
Yeah, you're audible.
Hello.
Oh,
Hello.
hello, you're audible to me.
Sir, am I audible to you? Then I can proceed with my question. One question.
Yeah,
Yes.
you're audible.
Yes, you are audible. You can speak.
What is your question? Ask the question.
Sir, am I audible to you?
Yeah, you're audible.
You are audible, please.
Sir, I mean, while we are preheating, I mean, will there be any change in pre-stream temperature with or without preheating? As I mean, you mentioned that one vortices, three vortices is being formed. So, will there be any significant change in pre-stream temperature?
What temperature?
I mean, mean temperature along the profile, along the temperature profile that is being generated.
What mean temperature? Then is trend will be same, but obviously the temperature is slightly more because already that preheated air means it has got more energy. Okay, so that's why the maximum temperature and also the mean temperature will be more, right?
While the profile will remain same, like as it if it was parabolic, then it will remain parabolic.
Yeah, it will remain like that. But the most important is that I mean the distribution pattern is changing. In one case, the temperature is only confined to the axis. Okay, towards the right, that is after a certain value of R, the temperature is remaining almost same as at which it is entering. But in case of preheated air, due to the several vortex formation and due to the no recirculation from the outside, the higher isotherm, that means higher some temperature in the range of 900 Kelvin or 1200 Kelvin is extended after the valve. That is the difference. Okay, that is good. Any other questions? Cannot hear you. That is. What is the problem? Why you are not able to hear me? So it is.
Maybe his system is something wrong. His Suman, is it not audible to you? Suman, hello, hello, Suman, hello, Suman.
I think that there is an internet issue.
Okay, okay. Because you told that when you are giving that heated flame, so already there is some energy. So that position of that stable flame, because under steady state, that position may alter because already that ignition energy is there. So when that flame is or the flame formation is there, that zone is may vary, but contour may be similar. Temperature distribution, contour, and obviously that thing. Sir, hello. Sir, is it correct for me? Yes, sir. Suman, are you? Suman, hello. Sir, maybe he cannot.
Sir, I cannot hear neither of you. I mean, it's breaking meanwhile. I cannot hear neither of you, neither you nor Bijan Kumar, sir.
These books, what sir has suggested, those books are very nice. That one is that during our student life, we have studied combustion, 3 books. One is Kenneth Kuo, Keating, and obviously sir has given another reference. These 3 books are very nice for fundamentals of combustion that studies. And okay. Anyone want to ask anything? Hello. Okay, then I would like to hand over this microphone to Madhurima, please. Madhurima.
Yes, sir. We are so much grateful to you to take our time from your busy schedule to grace the event. It's an honor to be here with you today. Thank you very much to our respected professor, Dr. Bijan Kumar Mondol, for imparting such great knowledge to us. We are highly obliged to it. Thank you, sir.
Sir, hello. Already.
And you are audible,
I am able
Suman.
to hear you. Suman has got
Sir,
some
again,
problem in his stage.
while the frame is, sir,
You are
once the
audible.
frame is, uptaking the, yes, sir, one more question. Once the frame is uptaking its height, will there be any diverging issue? Somehow, if the flame is not being channelized in its path, will there be any diverging issue within its domain, like converging, diverging? So will there be any diverging issue in it, within that flame?
No, diverging issue means what? It will take a bend in the other direction. It is, it has bended towards the center. You are taking towards the away from the center or something like that. Actually, he's not able
Away
to
from the
listen.
center, away from the center.
No, away from the center. No, that is not. That is called underventilated things. That will not happen because there is always a tendency because towards the right there is a wall. Okay, so there is always a tendency to bend towards the center. That is the nature of the field like that. So there will not be like that. But if that happens sometimes, depending upon the mass of this fuel and the air, okay, if it is differ very much, then it can happen also. But that is not desirable, okay, because in that can flame may extinguish after some time. Okay. So any other question from any other people? Otherwise, okay.
Anyone having any question? Yes, sir. Thank you, sir. Thank you, sir, for your extremely valuable lessons. And obviously, our student has got immensely benefited. Sir, we will keep contact with you continuously.
Yeah.
And obviously, we will carry out some joint research in our area. Sure, sir.
Your batch, first batch has come out or not?
Sir, our first batch came out. Our first batch came out.
Okay, then some of them will come to IIST Sipur for their intake. We will meet very soon, okay?
Yes, sir. Sure, sir. Sure,
Okay.
sir. Thank you, sir.
Okay, then can I leave now?
Yes, sir. Thank you, sir. Sure.
Okay,
Thank you, sir.
thank you. Thank you.
Thank you, sir.
Okay, so happy to meet you.
So with this, we are concluding this session. So we have another lecture today at 6:30 p.m. Professor Dr. Kaushik Ghosh, he will discuss on boiling heat transfer. That is also another virgin domain of research, because boiling heat transfer also, like this combustion research, so many concepts are there where really many things are yet to be revealed, because in that boiling zone, parboiling region, and those zones that temperature finding out, sometimes some inverse analysis are required. So this type of combustion research also, sir has pointed out what are the challenges associated for doing some experimentation on these combustion techniques, because sometimes some hazardous flames, hazardous poisonous gases are coming out. Sometimes that temperature measurement may not be accurate because of that temp turbulence and other things. And those things Sir has already initially pointed out. Also, that boiling heat transfer area, CFD simulation also having so many challenges. So definitely Professor Kaushik Ghosh from Jadavpur University, Professor of Department of Mechanical Engineering, Jadavpur University, he will deliver lecture at 6:30 p.m. So I am requesting all my beloved students to join within 6:20 to 6:25 p.m. for this third session. So thank you.